Okay, so applications of exponential formulas have to do with exponential growth and decay. Decay is often used in science to discover the age of something, so the decay of a certain isotope of an atom can tell you how old something is. But we're going to look first at exponential growth, and there are a few different versions of growth that we'll look at. The first one is A equals P times 1 plus r over n raised to the n times t. Now, a is really a function of t, so we could say the a sub t, or the a of t equals this formula. We tend not to, it's just a standardized formula. But a is a function of t. Since t is in the variable position or in the power position, we know that it is an exponential formula. And let's define the parts of this. So p, or a, means amount. That's as simple as that. It's amount at a given time. So the amount after 1 year would be plugging 1 in for t. The amount after 49 seconds would be plugging 49 in for t. So it has to do with time, and a is the amount of something at some time. P, in this case, this is a interest model, so the variables have to do with financial values, and P stands for principal. Spelled L-E. So it has to do with the principal. Oh, it is principal. Hey, who knew that? It's the same as your principal at a school. So principal is the amount invested, or the starting amount. Okay, 1. So what we're going to do is take the amount of money, let's put it into monetary terms. If I invest an amount of money, then it's going to multiply in its value every year depending on its interest rate and compounding rate. So if I take the initial principal and say once a year, I have to multiply it by the percentage of growth, right? So it's going to be some percent bigger than 1, because at the end of a year, I have to have my original amount. That would be that expression, right? My original amount plus whatever interest grew and however many times that interest was added into the total amount. So this is called a growth rate. This is called a rate factor. Oh, this is the growth rate. Sorry about that. And this is the rate factor, which makes sense because I'm multiplying p times this, which makes that a factor. N is the number of times it's compounded. And t is over a given time. So compounding is something we'll talk about in just a second. It basically means if you invest money, say I invest $100 at a bank at 3% interest for a year. At the end of that year, I could walk into the bank and say, give me my $100, my original 100, plus give me $3 more for the 3% interest. But sometimes banks do something to try to get you to keep your money there, or to get you to even invest it in the first place. They compound it throughout the year. So it's still 3% per year interest, but they will calculate that 3% in every quarter, say, so compounded quarterly. So every 3 months they'll compound it, basically meaning take 3% and add it to the principal, so that you're actually escalating your growth. Okay, very chatty way to say compounding. But let's do a problem. So Christy invests $300 in an account with 6% interest. So her principal, her initial investment is $300. and her interest rate, R, equals 6%, and we want to work in a decimal for percent, so 0.06. Making no other deposits or withdrawals, what will Christie's account balance be after 20 years if the interest is compounded? And then we get some choices. But let's start with the rawest form of this. If she never makes any other deposits or withdrawals, what would her balance be after just 20 years? Well, we have her amount, or balance, would be whatever her principal amount was times 1 plus 0.06 divided by, well, how many times was it compounded in that 20 years? It was only compounded one time, right? Because we're just doing pure interest rate. Compounding once times n, again 1 over t, which is 20. So if I stick this in my calculator, I probably don't want this calculator for that. Let's use this one. So I have 1 plus 0.06, which is 1.06. I'm going to raise this to the 20th power, right? So 20 is t. That gives me this decimal, which at this point I would probably want to go ahead and plug it in. Oh, I wrote p here. Sorry, I meant 300. So that's 300 times 3.21, which equal 3.21 times 300 equals $962.14. $962.14. So not a bad investment, I guess. You start with 300 and at some point in the future you have $962.14, but I could probably think of better ways to raise money. So let's look instead at compounded semi-annually. Semi-annually. Well, that means that n equals 2. Semi-annually means twice a year I'm going to compound that interest. So the same formula, A equals 300 times 1 plus, the rate is still 0.06, but I'm going to divide that by 2. 2 times 20. So that's 300 times 2.06 over 2. Let's go ahead and divide that 2. We can do as much as possible by hand. Once I have a common denominator, then I can put my 2 out here. Oh, I can't because that 2 has to be raised to a power. Times 40. So all of this over 2. So that's, I'm going to work across, 300 times 1.03 to the 40th power. So let's do the math on that then. Or the arithmetic, I guess. 1.03 raised to the 40th power times 300. $978.61. So compounding twice a year gets Christy a little bit more money in her savings. Let's look at daily. So for daily compounding, that means n equals 365 and a quarter, but we'll stick with the 365. And same formula, A equals 300 times 1 plus 0.06 divided by 365 raised to the 365 times 20. But that's 300 times 365 plus 0.06 divided by 365 raised to the 365 times 20. So let's put that on the calculator. 7,300. Okay, that sounds big. Sounds like a huge difference is going to be made now. So let's see. Inside we have 365.06 divided by 365. Raise that to the 7,300. Multiply that by 300. 995 and 94 cents. 995.94 cents. All right, so that isn't actually a big difference, but still, doing nothing at all, her interest compounding more regularly does change the value. It changes the amount of money over the course of that time that she has earned. So what if Christy said, nah, that's not really enough. It's not enough for me to come to your bank, even if you offer me daily compounding. I'm going to go to another bank. What if the bank came back and said, but Christy, we'll give you continuous compounding. That means every single second, instant, millisecond of every day, we're going to compound your interest. So continuous compounding has a different formula. You can find it derived in your textbook on page 163. It's a continuation of, or it makes use of the definition of the number E. And feel free to go look at that, but I'm going to just give it to you for the lesson today. A equals, let's put it up here because then it'll be up here where we want it. A equals P E to the RT. So continuous compounding has all the same values. A is the amount. P is the principal. It doesn't have the same values. It has the same variable definitions. P is the principal. E is a number. It's just a number. R is the rate. And T is time. So let's calculate Christy's value, Christy's money after 20 years of compounding continuously. So A equals, in her case, 300 times E to the 0.06 times 20. So I have 20 times 0.06, 1.2. So E to the 1.2. I know I have an E here somewhere. Nope, I have a natural log but not E. I could fake it, but let's pull up our other calculator. Remember 1.2 for the exponent. So I want E there it is, E to the, now on my calculator I have to just give it a power of 1, so E to the 1. Now I can come up here and just capture it. I'm going to raise that to the 1.2 and multiply that by 300. 996.0351. So that equals 996.4 cents, 0.04. So 996. So it's only a little bit more to compound continuously, but still it is more money. So this would be a really good time to generalize our formulas, because we did an example with growth, but you know from the previous lesson that growth and decay are exponential models, so our formulas have to reflect that. So general formula of growth and decay, N equals N sub O, that just means N naught. So in our principle, when we were talking about money, A was the amount that we had at any given time, N naught was the initial principal, but if you're talking about bacterial, you don't use principal, you use some number of bacteria. So N equals the initial N times 1 plus the growth rate, R, over T. So this has no compounding. This is a general form of a formula. And if R is positive, then this is growth. But decay, meaning that something gets exponentially smaller, the formula would be N equals the initial amount times 1 minus R over some given time. So the only difference between the two is that for growth, R is greater than 0, and for decay, R is less than 0, and if nothing changes at all, R would equal 0. And then our other formula, the continuous exponential growth or decay generalized formula, would be N equals N, the initial amount, times E to the K times T. That would be continuous growth. And that would describe something like a bacterial colony growing or a reaction in a test tube. And then N equals the initial amount times E to the negative KT would be decay. Continuous decay. Where the only difference is the sign on K. K is greater than 0 or K is less than 0. K is less than 0.